Hello, here's Miss Walsh, and today we're going to be talking about normal distribution. So what is normal distribution? Normal distribution is another distribution of how basically a variable behaves. It is not used for discrete, unlike binomial, but it is used for continuous variables. It's maybe the most important distribution. A lot of our behavior has this kind of shape where the biggest probability comes in the middle. So think about things like test scores. If you think about it, usually in a class, students will do okay mostly, and then you have some on the upper and the lower end. Same with the blood pressure. People to have normal blood pressure, some will have low, some will have high, but those probabilities then drop off. If you take heights of a whole 11th graders, there will be some sort of a mean height, and then some people over here will be super tall, and then these people are maybe not as tall. So really, a lot of behavior is represented by this very important distribution. And actually, there's even this machine about that if you're just throwing balls in, that also the way that the balls will fall, they will also be normally distributed. It's also called the Gaussian distribution for Gauss. So let's see how this is relevant to us. Right. What do we want to say about this? Well, first of all, over here in the middle, this is always the mean of the data, okay? And then depending on how spread out you are, you also have a standard deviation, which will make it more or less spread out, okay? Over here, those are your probabilities. That's the area under the curve. This is what we will be using for probabilities. Very important, if you're talking about something like times, waiting times, okay, because it's a continuous variable, let's say if you have something like 70 or 70.01 or 70.001, in this case, the value itself actually doesn't matter because it takes up such an infinitely small space in the whole distribution of infinitely many values, okay? All right, so let's just see what this is, okay? What can it look like? Well, again, as I said, in the middle, you will always have the mean of the distribution, okay? And then you remember that this right here, this is the standard deviation. So let's see if we can match these up. Well, okay, you can see that this is very much not spread out, right? So this is going to be, I'm just going to number these, 1, 2, 3, 4. If you want, you can pause and try to assign the distributions to the information yourselves, right? But you can see that here you've got the least spread. Remember, standard deviation is the average distance from the mean, right? So all of these values are pretty compact together, okay? So this will be our curve 1. Similarly, you can see the yellow one here is very spread out, right? So that'll be the one with your big distribution. All right, this one actually has a mean of -2, so that clearly has to be that one. And it has, a standard deviation somewhere in the middle. And then, of course, there's this last one that takes the second one. That'll be our red one, okay? So sometimes they're more stretched, sometimes they're less stretched. Okay, which curve is more likely to have high values? And again, if you want to pause, what do you think? All right, reveal, of course, that will be our curve number 3, right? Because you can see over here, you have the biggest probability of getting these high values. Which curve is more likely to have values close to the mean? Reveal, that will be our first one, right? You can see that most of the probability will be very, very close. So that's what it looks like. It's always symmetrical and super duper useful. Next important piece of information. It's not possible to actually calculate area. It's not possible to calculate the actual areas under normal distribution in any direct way, but it's easy to do so on the calculator. You will always, for normal, be using cumulative, okay? So you're not going to use the density function. Remember, you do use it for binomial, right, when you're looking for a specific outcome. But for the normal, because as we mentioned, the probability of one specific value is always 0, we always just do cumulative, okay? And there it is. It's probability. You go to cumulative, and then you go to normal, all right? So let's give this a try. The length of time patients need to wait at a hospital is normally distributed. That's your clue, okay, that this is what you will be doing. You will always be told that the variable is normally distributed, because if not, you don't know whether you can use this distribution. So for example, here, not all behavior is normally distributed. You can also have some that are skewed, and then all of the work that we're about to do would not apply. But this one is, so the first thing we're going to do is we are going to just draw this, okay? So just draw a nice little thing. Always label the mean here is 75, and then the standard deviation here is 22. Okay, find the probability that the patient needs to wait less than 60 seconds. All right, so this is your mean. So 60 is going to be below the mean, and they're asking us to do less than. So we're just going to shade this. Remember, the area are the probabilities, okay? Also, a word on notation. Just to translate this into mathematical language, this would be that x, which is your waiting times, is normally distributed with a mean of 75 and a variance of 22 squared. I know this is confusing if you remember, but this is just the way that we notate it, okay? So instead of putting the standard deviation, we always put the standard deviation squared. Okay, let's find this first result. So less than 60 seconds. So what you're going to do is you're going to go to the toolbox and then just do what it did above, right? So let's go to the toolbox, and then we're going to go to cumulative, and then we're going to go to the normal. Again, I'm going to hit help just to show you the bounds, okay? So you're going to enter the mean, you're going to enter the standard deviation, and then you're going to enter the value that you want it cut off at. Alrighty. 75, 22, and 60, okay? So what this is, and again, we're going to use normal notation in our writing as well. The probability that it's less than 60 is going to be 0.248. So what this is this is all the probability of all the waiting times up to and including, okay? Alrighty, probability that it is between 60 and 80. What you're going to do here is, again, we're going to go to the same thing. So I'm just going to hit enter again. And so except that now, always first mean, then standard deviation, and now just put in your lower bound, 60, and then put in your upper bound, okay? And so this is our solution. This is our probability that this is how long you're going to wait. Okay, and actually we should draw it as well, hey? Should be always representing our work. So so this is mu is 75. Remember the mean Greek letter is mu. And then between 60 and 80. All right, okay, so now more than 75. Again, we're going to be super keen and draw the graph again. And I have to explain to you how to do it when it's more than. All right, probability that x is greater than 75. So that would be somewhere here. Okay, what you want to do here is, again, you're going to hit this. When you need everything from a value and up to basically infinity, what we're going to do is we're just going to put in a really big number, okay? So 75 mean, standard deviation, then we're going to put 75, and then just like enter a really big number, like this, whatever. Oh, it's 0.5. If you want, pause and just think, why does that answer actually make sense? Alrighty. The reason that this answer actually makes sense is because 75 is our mean, right? Remember, there's always that symmetry, so you've got 50% on the right, 50% on the left, okay? And that's how you do these questions. I'm going to try another one. This is just a word about notation, right? So we already know mean, this is mu, this is the standard deviation, and this is always the way that it's written. I've mentioned this, but just to reiterate, okay, so this is variance. So here, what this means, this is variance. What that means that if this is your standard deviation, your variance, then we're just going to take that step to the standard deviation. Remember, you can get to standard deviation by square rooting the variance, and our standard deviation is 3. Okay, here we go. So again, if you would like to, just try it on your own, okay? And so what we need here is, I am going to just draw this curve. I'm a big fan of always representing the distribution. What's what I mean? 12. Standard is 3. Okay, and so what we need is we need something from 10 to 13. Okay, all right, let's do it. So again, you can just hit enter again, but I'm just going to do it again to remind you of the steps. Always cumulative. I say this again. Okay, and so now remember, first your mean, then your standard deviation, then your lower, and then your upper. And so what you get is you get 0.378. Good. All right, next one. The probability that x is greater than 9. Again, I would say pause, right? Interact with it. So this is 9. And then we know our mean, we know our standard deviation. Okay, then we need all of this. Okay, so again, it's bigger than, so it's going into infinity, okay? So we're going to do the thing that we did before with a really, really large value, okay? So it's 12, it's 3, and then we're going to hit 9, and then just hit a really big number. What will happen if you don't put the big number? If you just leave it as 9, the calculator will give you all of this, okay? The calculator always starts from the bottom up, okay? So we have 0.841. This makes sense. You can see that the probability is way bigger than 50%, right? You're covering most of the area. Okay, less than 12. I'm just going to speed it up so that the video is not too long. So for this one, what you're going to do is you just need to enter mean standard and then just hit less than 12, okay? See, and then what it does is it just gives you, okay, this is 0.5 again, duh, because it's the mean again.